Welcome to the lecture series on numerical methods, finite difference approach. And in the previous lecture, we have discussed this implicit and Crank-Nicolson scheme, and also for different schemes compatibility and convergence analysis we have discussed. And in the present lecture, we will just go for this stability of the explicit schemes, how you can check the stability of this explicit schemes or implicit schemes by using two different methods. Especially we are just finding this stability conditions. So first one, it is called matrix method, and second one, it is called Newman's method. So based on these two methods, we will just go for this checking of stability if a problem is given, and if we are just applying this explicit approach, whether this system will provide a solution or not. This means that solution it can provide, but whether that is feasible solution or not. So for this, if you will just go for this stability of the explicit scheme, especially as I have told that two schemes we will just apply. First one, it is called matrix method, and second one, it is called Newman's method. And in the matrix method, if you will just consider this same equation as in the form of like del u by del t by this equals to del square u by del x square here, then especially we are just obtaining this discretized scheme as in the form of like uij plus 1, this equals to r ui minus 1 j plus 1 minus 2 r uij plus r ui plus 1 j here, and where I is varying from 1 to n minus 1, and we are just computing these values at I j plus 1th level. So that is why these values at I minus 1 j and uij and I plus 1 j, it should be known to us here. Let the values of u at jth level are not correct, suppose, since along the boundary always it is fixed, but afterwards whenever we are just going for the computation, then maybe it is not correct, accurate, or you can just find that there is some difference from this exact value or the approximated value at each of the levels, and have certain errors. So the values of u at j plus 1th level can be calculated by using these values are also not correct, since we are just considering this previous time step level values for this like next step level of calculations. So that is why this error will get increasing. Let the true value is denoted by u and the approximated value is denoted by u star, and the associated error suppose by u here, so that the computed value can be expressed as in the form like u star I j plus 1, this equals to r u star I minus 1 j plus 1 minus 2 r u I j star plus r u star I plus 1 j. Since already we have explained here, we are just considering one true value as u here and the approximated value by u star. You can just say that this is the discretized solution, and this can be the true solution, means exact solution you can just consider, or sometimes you can just say that this is the numerical calculated value. And if you just subtract this true solution to the approximated solution here, then we can just find at I j plus 1th point the error will be E I j plus 1, and similarly this error propagated for each of these grid points are in the form of like E I minus 1 j, E I j and E I plus 1 j here, where I is varying from 1 to n minus 1. And we have known that along the boundaries the values are exact, since it is just provided the exact solution along the boundary which should be satisfied at each time level of the calculation. So we cannot change or we cannot differ from this boundary condition values at any step of calculation. So that is why we can just consider this E0j and Enj equals to 0, since the error associated along the boundary is 0, since it is provided exactly the values there above. And if you will just write these error terms for each of these terms starting from 1 to n minus 1, then these error terms can be represented in a matrix form as E1j plus 1 to En minus 1 j plus 1. Since E0 is fixed and it is 0 there, and En is 0 there itself. And if you will just put these values here, you can just find for the first state of calculation here, this is just giving you the 0 value here. So that is why the starting coefficient it will be 1 minus 2 r, and the next coefficient is r there. So remaining after like boundary points, you will have 3 coefficients, that is r, 1 minus 2r and r. So that it is just written in this form here. And your coefficients, if you will just see, that is just starting at first one is E1j, since E0j is always 0. So that is why E1j is the starting value and ending value it will be n minus 1j there itself. So in a matrix form, if you just represent this one, so Ej plus 1, since all of this j plus 1 is a constant here, but the variation in the ith level, that is at 1, 2, 3 up to n minus 1. So that is why you can just write Ej plus 1, this equals to Aej, since j is also remain constant for this level here. Suppose at some point t equals to t0, the error is denoted by E0, then we can just write E1, since starting j equals to 0, suppose we can just write E1 equals to AE0 here. Now E2 can be written as AE1. So recursively if you will just write, we can just write, then E1 is nothing but AE0, so we can just write a square E0, and if you will just proceeding in this manner, we can just find that Ek can be written as a to the power k E0 here. And we can just find that Ek is dependent on a to the power k here, since this error associated with this each of these sequences that is associated inside the matrix there itself. If elements of the matrix A become smaller and smaller tending to 0 or remain bounded as k tends to infinity, then scheme will be stable. Suppose if you will just consider A is the matrix here, since boundary values we are just restricted and we have taken it out, so we can just form a matrix that is of order n minus 1 to n minus 1, possesses n minus 1 distinct eigenvalues. Suppose this eigenvalue is a lambda s and a corresponding eigenvector is suppose Vs here, and s is varying from 1 to n minus 1. Then we can just write AB equals to lambda b, since these eigenvalues are distinct, so it can form this linearly independent eigenvectors. So that is why we can just formulate E0 can be expressed as a linear combination of all these linearly independent eigenvectors there, which can be written as like Cs Vs here, where Vs can be written as V1s, V2s up to Vn minus 1 s here. So if we can just express E0 in this form here, then we can just write a to the power k E0 as a to the power k minus 1 into AE0. So AE0 it can be written as like AB, suppose E0 is written as a summation of s equals to 1 to n minus 1 Vs here. So that is why if A can be taken to the inside the summation, we can just rewrite this AVs as lambda s Vs here, since in the previous slide we have just written that is as A Vs equals to lambda s Vs there. So finally we can just obtain after like k steps, we can just obtain Cs lambda s to the power k into Vs there. And for the stability, always we have to consider absolute value, or we can just take this determinant of a to the power k is 0, it should be less than 1, or we can just consider lambda s to be less than 1, where s is varying from 1 to n minus 1, or lambda maximum should be less than 1. Thus for the stability of explicit scheme, the modulus of largest eigenvalue of the matrix should not exceed unity. So if you just go for this Newman's method, so especially that is specifically written in a variable separation form, u of xt can be written as in the form of x of t and t of t, which can be written in a exponential form with this complex coefficients. Especially this is written in a generalized form as e to the power alpha t into a e to the power I beta x plus beta b e to the power minus I beta x, and we are just considering a, b, alpha and beta are constants there. So especially we are just representing this coefficient as a direct form here, that is e of pq, that is the error associated with each of these terms, that can be written as e to the power alpha q del t especially you can just say that that is the time difference error we are just getting, and del x means it is the space difference error we are just obtaining there. And the error formula for this like earlier problem, if you just discuss, then that can be written as in the form of e of p q plus 1, this is r e p minus 1 q plus 1 minus 2r EPQ plus R EP plus 1Q. If you will just use EPQ as the error term associated with this PQ node, then we can just say that this can be propagated to PQ plus 1 as in the form like e to the power alpha q plus 1 del t into e to the power I beta p delta x. Similarly, it can be extended to rest of the terms, that is as like first term, if you will just see here, that is p minus 1 q, then p q, then p plus 1 q. So, which is written in this form here, that is r e to the power alpha q del t into e to the power I beta p minus 1 delta x plus 1 minus 2 r e to the power alpha q del t dot e to the power I beta p delta x plus r e to the power alpha q del t dot e to the power I beta p plus 1 delta x here. So, if you will just compare these coefficients, especially if you will just see here, that is e to the power alpha q del t, since we are just taking the common r e to the power minus I beta delta x. So, that is why if you will just take common minus I beta delta x from here, so then we can just write this one as e to the power I beta p delta x from this term here. And this term we are just writing e to the power alpha q del t here. So, that is why inside this bracket it is just going like r e to the power minus I beta delta x here. And similarly, if you will just write this middle term, so that coefficient will come as 1 minus 2r, and the last term's coefficient that will just come as r e to the power I beta delta x here. So, if you will just neglect some of the terms at right hand side and left hand side, not neglecting that one, we are just cancelling both the sides since these are the common terms there. So, we can just write e to the power alpha del t, this equals to r e to the power minus I beta delta x 1 minus 2r plus r e to the power I beta delta x term. And e to the power alpha del t can be written as r e to the power minus I beta delta x, since we are just writing these two terms in a combined form, then this can be written as 1 minus 2r here. So, then e to the power alpha del t, this can be written as r, since we have known that cos x can be written as e to the power minus I x plus e to the power I x by 2. So, that is why it can be written in the form of r into 2 cos beta delta x minus 2r plus 1 here. And finally, we are just obtaining e to the power alpha del t, this equals to 1 minus 2r, since we are just obtaining here 2r cos beta del t minus 2r here. So, we can just take common from these two terms here, and we can just write this one as like 2r into cos beta delta x minus 1, and which can be expressed as since we know that like cos 2x can be expressed as 1 minus 2 sin square x. So, in that form, if you will just transform, then you can just find this one as 2r 2 sin square beta delta x by 2 here. And in the Newman's method, if you will just go for this stability, so then we have to consider this e to the power alpha del t should be less or equal to 1. So, if you will just take this left hand side is less than 1, this means that we can just write 1 minus 2r 2 sin square beta delta x by 2, it should be less than 1 also. So, this implies that if you just take the absolute value, it should be less or equal to 1. So, then we can just write this should be minus 1, it can be written this side here. So, this is the relationship it can establish as the inequality form, and the right inequality gives r greater or equal to 0 if you will just see, while left inequality gives r is less or equal to 1 by 2 sin square beta delta x by 2 here. Since if you will just see here sin square beta delta x by 2 is less or equal to 1, so the minimum value of r should be half here. This implies that the condition for stability of the explicit scheme is r less or equal to half. So, this restriction we should have to follow up whenever we are just applying these explicit schemes. So, for a practical example, if you will just consider, and if you will just apply this stability criteria, if it is not justified and how it is just coming to the picture, that we will just discuss in this example. So, if you will just go for the solution of this partial differential equation here, so that is in the form of del u by del t equals to del square u by del x square. So, especially you are just writing this is del x square here, where x lies between 0 to 1 and t greater than 0, with boundary condition u of 0 t this equals to u of 1 t equals to 1 here. The boundaries, it is prescribed at 0 and 1 as 1 there, and the initial conditions, that the same symmetry condition we are just assuming here also, that is at x equals to 0.5, the symmetricity will be maintained, that we will just take this condition as 2 here, and del t is given as 0.04 here, and the question is asked to solve this problem using explicit scheme. So, we can just show that whether explicit scheme will provide a solution or not in a feasible sense. So, if you just consider here del t equals to 0.04, then we can just obtain r as del t by del x square, which is written as 0.04 by 0.04 as 1.0 here, and the explicit formula for this scheme can be written in the form like uij plus 1 equals to ui minus 1j minus uij plus ui plus 1j, where I is varying from 1 to 2. Since the value oscillate at x equals to 0.2, if you just see this problem section here, then we can just find that whenever we are just applying these conditions here, then we can just obtain along the boundaries we have like a 1.0, 1.0, 1.0, all these boundary conditions are there, and along these boundaries if you just see this is 1.0, 1.0, 1.0, it is just coming over there. But if we are just computing these values at 0.2th level, it is just giving you 1.4. Due to symmetricity, the same value it is just appearing at 0.8 level also, and whatever it is just coming at 0.4 level, the same value it is also coming at 1.8th level here. And if we are just proceeding, the same value again we are just getting at like 0.2th level, and the same value we can just obtain at 0.8th level also here, and due to symmetricity 0.4 has the same value as of 0.6 here. But if we are just proceeding further, then you can just find that there is a oscillation, it is just occurring here. This means that it is just coming decreasing down again, 1.0 it is just coming, this satisfies the boundary condition again, and 1.4 if you are just getting the symmetricity, we are just getting along the 0.6 as 1.4 also. This means that the temperature, it is just at the beginning it is just starting at 1.0, suddenly it is just getting increased close to the boundaries, then it is just getting decreased there. So, at 0.16 level if you will just see, again this is getting decreased, and at 0.12 level if you will just see, again it is just increasing. So, this represents a oscillating profile here, and whenever we are just proceeding towards like after this 0.20 level, we can just find that this is just going to negative level here. Negative level means since we are just supplying heat from the boundaries, so the core temperature cannot go down the like a negative sense. Since if you are just supplying heat from the boundaries, so always in a common sense if you will just take like a water pot suppose, and if you are just supplying the heat along the boundaries, the water will be getting heated it off, and along the core section you can just find that this temperature will grows up, it will never goes down there. But in this sense we are just getting that the temperature is going down and it is just achieving the negative value after certain time steps. So, it is not signifying any physical sense that this stable solution we are just obtaining, since at the present solution we can just visualize first it is just oscillating and suddenly it is just approaching towards a negative value. Even if the temperature is supplied or heat is supplied along the boundary, so this physical scenario will never happen that in the core of this section you can have a negative value there itself. So, that is why it is just we have the statement that since the value oscillates at x equals to 0.2 and later the temperature becomes negative at t equals to 0.24, which is impossible because the temperature is unity along the boundary here. So, if you will just see our condition here also, this means that we are just neglecting one of this inequality in the first half. That means that if we are just considering r is greater or equal to 0, when the left inequality becomes this one here. But if you will just consider like r less or equal to 0 here, so we do not know what it will happen there over. So, that is why there is a restriction that whenever you will have like r less or equal to half only, you can just find that the system is stable and we can have a feasible solution there. Thank you for listening this lecture.